So, in the last class we learnt about special matrices. We saw symmetric, orthogonal, Hermitian and unitary matrices, and we briefly talked about things called similarity transformation. Okay. Now, today I am going to talk about spectral decomposition, matrix diagonalization, normal modes, and then some more a few other things about matrices I will mention. Okay. So, we will start with spectral decomposition. We will restrict the discussion to square matrices only. Okay. And now sometimes what happens is we saw that a unitary transformation can take matrix A to A tilde, okay, and what you say is that unitary transformations on a space preserves the norm of the vectors in that space. Okay. So what you are doing effectively is like you are rotating the coordinate system. Okay. So by rotating the coordinate system, now your matrices which become different. Okay. So it's like looking at the matrix in a rotated coordinate system. Okay. Now why is this useful? When would you imagine this to be useful? So you can imagine that you take your coordinate system, you rotate it to such a way, okay. So this is a rotation of coordinates, okay. So you are looking at the matrix in the new rotated coordinate system, okay. Now you can imagine that you do one particular rotation, and in that rotated coordinate system your matrix becomes diagonal, okay. So can you rotate the coordinate system in such a way that the matrix that was initially not diagonal becomes diagonal, okay. Now why are we interested in diagonal matrices? Because diagonal matrices, the eigenvalues are easy to calculate, okay. So this is one example of transformations that you often do. Okay. So one classic example from chemistry is in the moment of inertia matrix. Okay. So in general, if you have a polyatomic molecule, okay, then it has 3 rotational degrees of freedom. Okay. If you want to write those rotations, okay, as 3 independent rotations, you have to find something called the principal directions. Okay. So what do you do in calculating the principal directions? So we look at the moment of inertia matrix, okay, or actually it is a tensor. Okay. So this tensor is defined the following way. So you call I x x equal to sum over I m I. What we are thinking is that you have a rigid body, okay, and it has various point masses, okay. So these are the various point masses, okay, and these are located at some coordinate r, ri, okay. So these are the coordinates, and each point mass has xi, yi, zi, okay. Then you define Ixx as mi times ri, which is with respect to some point which is usually taken as the center of mass. So the origin is usually taken as the center of mass. So you take ri, which is the distance from the origin, minus xi, the x coordinate of that point, whole square, and usually these point masses are the actual atoms, okay. So if you have a polyatomic molecules, then you do for each atom, so you sum over all the atoms, okay. So this is the xx component of the moment of inertia matrix, okay, and similarly you can do for yy and zz, okay. So and then you have the xy component, okay, which is defined as minus sum over I mi xi yi, okay. So what this moment of inertia matrix looks like, it looks like this. So you have I xx, I yy, I z z along the diagonals, and then you have I x y, I x z, I y x, I y z, I z x, I z y. Okay, so this is what your moment of inertia matrix looks like, and clearly you can see that I x y equal to I y x. Okay, so therefore the matrix is symmetric. Okay, so it is a symmetric matrix. Okay. Now this matrix appears very naturally when you are describing the rotational, when you are writing out the rotational Hamiltonian for a for a polyatomic system. Okay. So this moment of inertia tensor appears naturally. Now the main issue is that if you just use some arbitrary coordinates, then this moment of inertia matrix is not diagonal. If it is not diagonal, then it becomes very difficult to write to actually calculate the rotational energy. Okay. So what is done is that you transform the coordinates. Okay. So you transform the coordinates till this matrix becomes diagonal. So what is done is you go to some coordinate some coordinate which I represent by I tilde is a moment of inertia in the transformed coordinate. Okay, and this is done by using some sort of similarity transformation. Okay, so I'll just put R transpose. So this is a rotational matrix. Okay, and if you do this, okay, remember for a rotational matrix is orthogonal. So this is nothing but R inverse. Okay, so what you are doing is you are rotating the coordinate system. Okay, and in this coordinate system, so rotate so that I tilde is diagonal. Okay. So what have we done? We have taken this initial matrix which was not diagonal and essentially rotated the coordinate system so that it became diagonal. Now in this coordinate system, okay, you will have three directions. You will have the coordinate axis. Okay, so the coordinate axis are basically the eigenvectors. Axis in transformed coordinate system are the eigenvectors. I'll just call them Vi, eigenvectors Vi. Okay. So what we have done is we have rotated them, and when you find that it becomes diagonal, then the axis that you have in this rotated coordinate system is nothing but the axis points along the eigenvectors. So what you can write this I tilde, once you have this, you can write it as sum over all the eigenvectors. You can write it as lambda I Vi transpose. Okay. So if you take a vector and multiply it by its transpose, okay, then you will get a matrix. So it's like taking one vector that looks like this and multiplying it by its transpose that looks like this. So you will get a matrix. Okay, and so I tilde you can write as lambda I Vi transpose. Okay, and so this procedure of writing a matrix in terms of its eigenvalues and eigenvectors is a very general procedure, and this is called spectral. This is either referred to as diagonalization or spectral decomposition. Okay, so you write this matrix in this form, and this is called a spectral decomposition. Again, this is a very commonly used technique. Okay. So what we say is that when you do a spectral decomposition of a matrix, you are basically finding out its eigenvalues and eigenvectors. Okay. Now we look at one very practical application of eigenvalues and eigenvectors, this is what is called the normal mode. So far we talked about rotations. Now if we talk about vibrations of molecules, of polyatomic molecules, okay, these are expressed in what are called as normal modes. So in some sense the eigenvectors for vibrations of polyatomic molecules are exactly the normal modes, just as what we saw in this case, that that when you transform your moment of inertia into a diagonal matrix, okay, then the rotational matrix becomes diagonal. I forgot to mention, but these directions are referred to as principal axis. And so your I tilde, I should mention, that looks like IA, IB, IC. So in this transformed coordinate system, it just looks like this. It looks like diagonal in the with the and IA, IB, IC are called the principal moments of inertia. Okay, so IA, IB, IC are called principal moments of inertia. So when you convert it into a diagonal matrix, these axes, the A, B, C directions are called principal axis. Okay, now what we are doing is a very similar thing, but we are doing for vibrations. Okay, so for rotations you have these principal axis and principal moments of inertia. For vibrations of polyatomic molecules, what you have is what are called normal modes. Okay, so what is a normal mode? So let us take a very simple example. Okay, this can be, you can think of it as a CO2 molecules. So if you take a CO2 molecule, okay, so it is a linear molecule, okay, and we will just restrict to one dimension, 1D. Okay, so that means you just have this has coordinate x1, this has coordinate x2, this has coordinate x3. So you just have 3 coordinates. Okay. Now what you will do if you want to express these vibrations, what you will say is that you will write the equations of motion for the first particle. So the first particle, the equations of motion will be m, let me take the mass of this as m, mass of this as little m, mass of this as m. Okay. So my equation of motion will be m d2 x1 by dt square, okay, is equal to minus k, it should minus k, and let me take for convenience that this has a spring constant k and this is k. So when you are modeling vibrations, you think of this bond as having some spring with spring constant k. Okay. So if I write this as minus k x1 minus x2. Okay. So this is the equation of motion for this mass, and you can see that it so x1 is in some sense it is it really reflects the displacement from the mean position. Okay. So you can think of x1 as a displacement from the mean position. Okay. So x1, x2, x3 are displacements from mean position. So what I mean is if you are at the mean position, okay, then basically x1 will be 0, x2 will be 0, x3 will be 0. So when x1 equal to x2 equals x3 equal to 0, you will all the atoms will be in their mean positions. Okay. Now I can write for x2, I will have something like this. x2 minus x3, and I can write for the x3 particle, for the third oxygen atom, I can write m d2 x3 by dt square, this is equal to minus k x3 minus x2. Okay. So, these are my 3 equations of motion, okay, and I can write these equations of motion in matrix form, okay, and what I'll write is I can write this as so instead of writing this second derivative with time, I will just use x1 double dot, x2 double dot, x3 double dot, okay, and this I can write as the following matrix. So, I can write it as so now x double dot is minus k by m x1. So, minus k by m, and then it has plus k by m x2, and it has 0, and then here it is you have plus k by m, k by little m, and you have for x2 you have minus 2 k by little m, and for x3 I have k by m, okay, multiplied by x1, x2, x3. So, all I have done is I have just rearranged this and written it in matrix form, okay, and then here I will have 0, I will have plus k by m, and I have minus k by, I have minus k by m. So, I wrote these 3 equations in this form, okay, and what you want to do when you calculate the normal modes is this is a, I mean when we do differential equations we will see this is a system of linear second order differential equation with constant coefficients, okay, and the general solution can be written as minus omega square x3, okay. So, it is like this is the matrix version of solving a simple harmonic oscillator, one dimensional simple harmonic oscillator. So, what does this mean? Now I wrote this in matrix form, okay, and what you can immediately tell is that omega is nothing but an eigenvalue of this matrix, okay. So, what we want to find out first is what are the eigenvalues and what are the eigenvectors, okay. So, if I give you this matrix, then you know that you are referring to this system. So, as soon as you have this system CO2, okay, you can write this matrix, and what we are doing is nothing but calculating the eigenvalues and eigenvectors, okay. So, when you calculate the eigenvalues and eigenvectors, you will get what are called the normal modes, okay. So, these are nothing but eigenvalues, and these are the corresponding eigenvectors, okay. So, what we did, we had only this differential equation, okay. Now, when you set it to minus omega square x1, x2, x3, you are basically asking for the eigenvalues and eigenvectors, okay. And I will not do this in detail, but you know by simple calculation, okay, we can get 3 eigenvalues, okay. The 3 eigenvalues are omega square equal to 0, omega square equal to k by m, and the third eigenvalue that you will get is omega square equal to k by m plus 2k by m. Okay, so these are the 3 eigenvalues you will get, and the corresponding eigenvector. Okay, so these are your eigenvalues, and the corresponding eigenvectors are, so for omega square equal to 0, your eigenvector will basically have x1 equal to x2 equal to x3. Okay, remember so you can take any value for x1, x2, x3, but basically they should be the same. Okay, so remember eigenvectors can only be determined up to a constant, they cannot be uniquely determined. So in this case you have x1 equal to x2 equal to x3, and now you can see that if x1 equal to x2 equal to x3, then each of these 3 atoms is being displaced in the same direction by the same amount. Okay, so each of these atoms is being displaced in the same direction by the same amount. So, this actually refers to a translational. This refers to a pure translation. Okay. So, so it is not actually a vibration, this is one mode when all the 3 atoms are moving in the same direction. In this case your eigenvector looks like x1 should be equal to minus x3 and x2 equal to 0. So, when you solve for this eigenvector you will find that x2 has to be equal to 0 and x1 and x2 have to be opposite signs. You can take any multiple of this, but they have to be opposite signs, and this is what is called a symmetric stretch. So, what you have is that your center carbon atom is fixed, and you have these is moving in one direction, this moving in the other direction. Okay, the two oxygen atoms moving in opposite direction. So, this is a symmetric stretch. Okay. Now, the third one, okay, this has eigenvalue. So, it has x1 equal to x3 and x2 equal to minus 2 capital M by small m x1. Okay, and this is what is called an asymmetric stretch. Where your 2 oxygen atoms are moving in the same direction. So, they are moving in the same direction by the same amount, and the center atom is moving in the opposite direction by some other amount, your carbon atom. So, this is your asymmetric stretch. So, what we can see is that just by calculating the eigenvalues and eigenvectors you can get the normal modes, and you can identify what is a symmetric stretch and asymmetric stretch. And what we see is that the normal modes of this this linear CO2 molecule, okay, we restricted the CO2 molecule to move only in one direction, okay, and we naturally find that these are the 2 normal modes. Okay, so, symmetric and asymmetric stretch are not things that we choose for convenience, these are the natural normal modes of this system, and you can do this for multidimensional polyatomic atoms too. Okay, now I will just before I end this I will just mention a couple of things. There is something called an ill-conditioned matrix. Okay, so this is this has to do with solvability by numerical methods. Okay, so, numerical methods are a very integral part of matrices. In fact, there are very large number of numerical methods that involve matrix operations, and now a matrix is said to be ill conditioned. So, if it is very sensitive, if the results are very sensitive to the values. Okay, so what happens is often you are trying to solve a matrix equation. Okay, so if you have Ax equal to b, okay, now you just make a small change in A. Okay, if you get a very large change in x, then you say that matrix is ill conditioned. So, small change in A leads to large change in x. So, x is a solution. Okay, so you are solving for x, and what you say is small change in A or B, okay, will leads to a large change in x, and so this is called an ill conditioned system, or an A is said to be an ill conditioned matrix. Now, a matrix, there is a way to check for this ill conditioned matrix by doing something called the condition number. So, I will call this k of A. This is the absolute value of the largest eigenvalue divided by the absolute value of the smallest eigenvalue. Okay. So, if k is large, then A is ill conditioned. Okay. Now many times you are evaluating, you are solving these matrix equations by some numerical procedure. Okay. Then you have to really worry about whether the matrix is well conditioned or ill conditioned. Okay. So this is one thing about matrices that I want to mention. The other kind of matrix I will mention is what is called a sparse matrix. So, a sparse matrix has very few non-zero elements. Okay. So, that means you have a matrix where you have essentially you have some numbers C1, C2, C3 and most of it is 0. Okay. So, most of the matrix is just 0, okay, and you just have a few numbers that are non-zero. Okay. So, you might have C4 here somewhere there. So, a sparse matrix has very few non-zero elements. Okay. So, now again there are very many special numerical algorithms for calculations involving sparse matrices. So, if you know that your the matrix that you are working with is a sparse matrix, then you can come up with very nice new numerical methods for these systems. Okay. I'll just mention again that many times matrix operations are done numerically. Okay. So, suppose you want to you often deal with matrices are very large. Okay, when I say very large, you might deal with 10 raised to 6 by 10 raised to 6. So, million by million matrices, and you cannot calculate the determinant the usual way or the inverse the usual way. So, all operations, so determinants, inverse, etc. These are eigenvalues, eigenvectors. All done using numerical methods. Okay. And many of these numerical methods are actually iterative. That means you start with some guess and then you keep correcting it and you go on. So many methods are actually iterative. It means start with some initial guess and keep on improving. Okay. So, what I just wanted to tell you is that numerical methods are an integral part of matrix methods, okay, and these are some of the most important things that people do in all branches of science and engineering, okay, and I will conclude this discussion on matrix. Now, in the next lecture, I will do one illustrative problem involving rotational matrices using matrix of rotations.